Our last speaker today is Jim Meacham. Jim has been in the energy industry for over 10 years. He's focused on advanced energy solutions in new and existing buildings. He is both an M and an E, mechanical and electrical engineer. He runs the energy services group at CTG Energetics. And CTG is a large and respected firm in this field that has recently merged with Cadmus. So, Jim?
Thanks, Mark, and thank you, John, for the good introduction here. I'm going to be talking about ventilation rates in commercial office buildings, but I think some of the conclusions, at least at the high level from an energy perspective, are very similar to what John found, but for different reasons. So I think it's important, especially for the practicing mechanical engineers in the room, to see some of this research that was conducted as a part of the Codes and Standards Enhancement process with HMG and PG&E. So some of the learning objectives there. And our outline for today, I'll talk a little bit about the study. We started by doing a little bit of best practice investigation around how best to do these measurements, since we were going to be in the field doing a lot of outside airflow measurements. We wanted to make sure we got that right and understood the ins and outs of that. Then I'll jump into the results, but more quickly into what are driving some of these ventilation issues that we have all observed in the field, and some recommendations for us as an industry on how to address those things. So as I mentioned, this work was done kind of as an offshoot of some of the non-residential codes and standards enhancement work that we were doing with PG&E, and included a physical performance survey, pretty rigorous performance survey in the field, all over the state, different systems that we could get access to, 33 tests in total. And we were originally looking at demand control ventilation systems to see what the impact of having demand control ventilation was on minimum ventilation rate performance, but it kind of morphed into something different that you'll see here based on the data that we found. But the first thing that we did was really try to make sure that we were going to go to the field using the best practices, and that we understood and had a good protocol for how we were going to do these measurements in the field. So we worked with the TAB industry folks and all the good papers that have been written around flow measurement testing. But then we developed a methodology to go do some evaluation in the field for our purposes, since we were focused just on outside air flow testing, which has its own kind of set of velocity profiles and things. So we looked at a few different methodologies, more than this actually, but the dreaded temperature split, velocity matrix traverse, which is basically just a 1x1 square field of pitot tubes. So you get an average velocity flow over a 1x1 square, hot wire anemometer, and then the flow hood. So I won't beat this to death, but we looked at a bunch of different testing configurations with all those pieces of all those instruments, shrouding to block exterior wind issues, different measurement locations, interior and exterior to the units, and then different fan modes for the units, going from minimum flow all the way to maximum flow. And there's a lot of data on this particular slide. It's really looking at the accuracy versus the precision of the different measurement techniques. So we're looking at how much variation do we get between measurements across the different measurement types, and then a relative accuracy towards a known calibrated flow station in this particular unit. And I'm sure these slides will be available afterwards, so I can't spend too much time here describing this. But the basics of it are, we want is the highest accuracy with the best precision that we can, and there's trade-offs for those when you look at these different types of measurements and locations and techniques. And what it comes down to is what we kind of knew going into the study, but was confirmed, that the hot wire and the velocity matrix are really the best performers for these tests. We know that. One thing that became evident in terms of the variability of the testing is that the velocity matrix really was not very repeatable down below 250, 200 feet per minute, but the hot wire was very repeatable in that flow regime. We also found, obviously, that wind has a big impact when we're trying to take these measurements, and we saw huge variability for those systems that were wind affected on the roofs. So one of the key takeaways from this is design, and I'll come back to this, but just to seed the thought for us designers, designing for consideration of how this outside air minimum flow is going to be controlled and tested is really critical. And we'll talk a little more about that. We didn't use a flow compensated hood or pressure compensated hood. So flow hood was out for a variety of reasons, obviously. And temperature split really has air stacking problems, and you have to have some absolute reference for measurement to make that work. So getting into the test itself, we looked at a variety of different system types. We were looking at multi-zone systems, single-zone systems. We looked at both built-up and packaged multi-zone systems. And we took multiple tests within each system so that we could get kind of an average performance measurement. We also looked at systems that had different types of flow control strategies, and we'll look at the data there. For all of the variable volume systems, we were testing across the flow regime. So we wanted to know how are they performing both at what we think our minimum flow would be on the system, and then at maximum kind of full cooling flows for the system. And what we found was that in general, almost all the systems are significantly overventilating compared to Title 24 ventilation requirements, which we know in general for office buildings are even ventilate a lot more than ASHRAE 62.1. So there's a breakdown here. The bottom line is we observed about 60% more overventilation compared to code than what was required. And then you can see some differentiation in there between the different types of systems. I think one of the interesting things, and we'll dig into these data a little more, but the single zone system, obviously the worst performer without any dynamic controls. But the packaged multi-zone systems, even with fixed damper positions, did a lot better than the built-ups. And shuffling those data a little bit different, what we find in terms of the across the testing, that 64% of our tests we found the systems to be overventilating outside the prescriptive plus or minus 10 that the Title 24 acceptance forms would dictate as the ventilation compliance range. A few of the systems, about a quarter of systems actually underventilating, and a few that were actually compliant. So one of the important things that we found through this study, and is kind of somewhat addressed in the code, although not universally, is this notion of dynamic control of the minimum ventilation. So we're talking about just the minimum outside air ventilation. And for those systems that have dynamic controls, we find what we would expect, that we have a lot less overventilation than those that just have fixed minimum damper positions, which is the predominant system type in the world. We're talking about a factor of 3 times more overventilation, at least, for those systems. And if you dig into it a little further, the data become even, I think, a little more compelling in terms of what we need to do as an industry. And that is, if you look at the difference between minimum and maximum modes of these variable volume systems, so kind of nominally heating to cooling, if you want to think about it that way, you see a huge difference in those systems that don't have the dynamic controls, which is what we would expect, but I think really important outcome. So for the dynamic control systems, we see a relatively slight increase as we move from the minimum flow, total flow, to the maximum total flow, because the dynamic controls are nominally doing what they should be doing to control that amount, that ventilation rate. But if you look at those with the fixed minimum damper positions, again, the predominant system that we see in the field, it's doubling as we go from minimum to maximum, and we know that maximum is happening at our peak cooling time in the summer, when we definitely don't want to be bringing in 100% more outside air than we need to be bringing in. So what's driving this? I mean, there's a lot of factors here. One is just improper air balance techniques, or out of calibration hasn't been revisited in the last few years, and there's a few things that are making that happen in the field. One is that the flow measurements are difficult. When you're using a hot wire, this is kind of a scientific instrument. Not everyone is adept at how to use some of these devices, and measuring areas of dampers that are open and getting the right net free area calculations. These are difficult things and subject to a lot of error as you stack some of these different factors that go into calculating the amount of flow that's happening. The other thing that we're seeing is the outside airflow is typically configured under one set of conditions. So when the air balance folks come in, they're usually calibrating at one point, setting the system up at one point, as opposed to looking at the range of minimum and maximum flows for a variable volume system. So you have a system that may work or come close to working at that point, but as soon as it's off that point, we're either under or over ventilating. And one of the things that's driving both of these issues, or at least the first one in terms of having the flow measurement set right, is it's sometimes very difficult to actually get in and measure these systems. So depending on the design, it can be difficult to get to the dampers, to get good measurements, to get inside the systems and get accurate measurements. The other one is a lack of dynamic control. So a lot of systems just simply never were specified to have any type of dynamic control of the minimum ventilation rates. There's a lot of ways to do it, either just a simple 2-point control. You could easily set up your system to modulate from one damper position to the other across the range of the supply fan as a coarse way of making the system have a dynamic response to the changing of the total volume flow of the system. Some we see out there with a direct airflow station, so we're using like a Ruskin damper situation and measuring the airflow directly and using that as a feedback signal. Differential pressure control between the mixed air plenum and the outside condition can be a way to do it. We've seen differential flow calcs between supply and return fans. That tends not to be very accurate. Could be calibrated, but is dependent on a lot of other factors in the building, so not necessarily a good way to do dynamic control. One that we found, too, with the systems that actually are using dynamic controls is just integration issues associated with those controls themselves. So coordinating the sequences between what the return or exhaust fans are doing and the return mixed air damper linkage is a real challenge. Loop tuning, so it's not hunting, and you have multiple pieces of the equation here between the dampers and the fan speeds, and building pressure, all fighting each other to try to maintain equilibrium across, solving for multiple things. So it's not necessarily that easy. And one of the things that we found as a result of the research is that dedicated minimum dampers have a huge impact on our ability to both measure and control outside air. So you can imagine for a large air handling unit that's got only one set of dampers that's used for both minimum ventilation control and economizing, taking airflow measurements across a large filter bank that's slightly open and actually getting accurate airflow measurements is quite difficult. So having a small dedicated minimum outside air section that's always open and then a large economizing section that is only open during economizing mode can really have a huge impact on our ability to take these measurements. So it increases the velocities across that damper, which makes it easier to get more precise and accurate measurements. It makes it easier for the flow stations, if you're going to use that, or some type of differential pressure control to work. And we have more controllability of separate dampers now as opposed to one damper bank. So some of the conclusions here, we noticed obviously that many systems significantly overventilate, especially during peak flows, peak times. And the takeaway from that, from my perspective, is, and being in the commissioning business, we see a lot of these sequences. We need to make sure that the spec for sequence of operation that includes dynamic minimum ventilation control is included in all of our projects. And it's kind of implicit in Title 24 for California, but not necessarily explicit. We still see a lot of projects that come through that don't have a sequence that specifically defines that mode of operation for our systems. And then we need to be cognizant as an industry of how that minimum flow rate is going to be controlled. Using the dedicated minimums, making sure that we have access. There's a method for taking the measurements and getting accurate measurements, and how the implications of using return fans or exhaust fans in the different damper systems for how that is going to be able to be controlled in the field. We need to bring that into our day-to-day practice. That's it.
Thank you, Jim. We're going to take some questions now, and I can't see the mic, so you'll have to come up to it and wave at me. But I'm going to start with a question for Jim. The graph you showed a substantially different rate of overventilation in fixed versus dynamic. and you listed a bunch of issues with commissioning and control, et cetera. But it seems to me that one thing that might be driving that is plain and simple oversizing and misunderstanding of actual building load in the design. Is that true? Here.
Well, I think what's actually driving that is probably that it was never configured correctly. So even if the designers did their job on the ventilation calculations, which is what we're talking about here, it's just the configuration of how it's originally set up. What is that minimum damper position, and at what point is it configured? That's what's really going to drive the operation. And then you have all the other. These were all relatively. I didn't mention they're all relatively new buildings. I think since 2005, all the systems that because we wanted buildings that had been permitted under the Title 24 2005 code. We had some that were 2001 in the study, but all relatively new buildings. So if you assume that the calculations were done correctly, and then you're there. But we were only comparing to the actual Title 24 calculations as provided on the documentation. So,
yes.
Please state your name too.
Sure. Senthil with Partner Energy. This is a question for Jonathan and Mark. That was a nice presentation. When you it's a couple of questions. First is the how you come up with the low energy use building and a high energy use building. Is there any baseline you're using?
It was a range of baselines because each one of those variables we had to decide, okay, what are we going to say is the high performance and what is the low? So it's a combination of just experience, other studies. We used the 189 standard for some of those inputs. It came from a range of different places. Each variable was different.
Okay, because the reason I asked that question is because every building, the controls plays a major part on it. I know you guys done the HVAC, the lighting, and the envelope, because if you have a turbo chiller, is operating more efficiently than if you're not controlling it right, it's not going to give you anything. Did you guys look at the controls as part of it?
Controls are hard to model, broken.
Yes, yeah.
And so we came up with some proxies for what we considered to be broken controls in the analysis, but we realized that there was a whole bunch more work to be done to zero in on some of those issues, especially controls. The other thing I would say on the baseline, whenever we had data to make decisions about baseline, we used it. So, for example, NBI's recently done some plug load analysis work. And so we used the range of findings we had from that study for low, medium, and high. For the insulation, we used 189 as the best insulation and ASHRAE 89 as the worst, and 90.104 or 07 as the baseline. I can't remember. So we tried to use boundaries that made sense, but there were certain things where it really mattered what we decided. For example, we analyzed a data center, and we put a 600 square foot data center with a plug load of 75 watts a square foot, I think, or was it 40? And that was one of the biggest factors. And so just a tiny change in assumptions about that, which were based on nothing, totally changes the size of that bar, but it's always big. So if that gets at you.
Okay, thank you.
I'm Dennis Peltz with RTKL. I have a question for Jim. Could you comment on air quality sensors and how good they are and any problems you've seen with them?
Sure. So I guess there's a couple different systems. If you start with just the basic CO2 sensors, there's actually been a lot of good recent research by Lawrence Berkeley and the Iowa Energy Center about CO2 sensors, how effective they are. One of the most interesting things to me is one of the recent studies found that a lot of these sensors are failed from the factory. They're getting better, but a significant percentage, I think some of the work that Bill Fisk's done at LBNL suggests that is upwards of 30% or more of the sensors in one of their studies they did were actually not within at least the California Energy Commission's definition of within calibration, which is plus or minus 75 ppm. So there's definitely, and Mark I can see wants to add something to that. So there's definitely, I think the application is what's really important. So how it's used, where it's used, and then the operations and maintenance strategy that's wrapped around it to ensure that it stays within calibration it's in the nuances there. In general, I just, from my opinion of it is, we're trying to use way too much CO2 demand control ventilation systems and not in necessarily the right applications, and we need to confine it to those applications where it makes sense, where we're really just using it in the high density, high occupancy, intermittent occupancy places that we can do something about it. Otherwise, I think it just adds more complication to the overall O&M strategy and more equipment and more sequences to break. So I think from a designer perspective, I would say simplicity. There's new systems, not necessarily new anymore, but broader indoor air quality management systems out there that sample all the other indoor air pollutants and go way beyond just CO2. They're multi-point sensors and can do a lot more than just a standalone CO2 system. But I don't think there's enough study out there yet as to speak to how effective those are relative to the standalone CO2 sensors.
I'm just going to really quickly add a related issue on economizers. NBI was involved in an eye-opening and somewhat famous study that suggested that 75% of economizers did not work as designed within 5 years of installation, including ones that were just installed. And we were involved in technical committees with manufacturers on this for a while. And at one point, one of the major manufacturers of economizer controls admitted that their controller had never worked. They knew it didn't work, and it wasn't even, even the way it's designed, it never could have worked that way. It was not designed for that, and it's been used as the main controller for years. They announced this when they finally came out with one that actually did work. So,
Ibrahim Nufiz, University of Dammam, Saudi Arabia. I have a question for Jim. Do you have any data indicating the energy consumption because of over-ventilated buildings? Thank you.
For this study, we didn't do the energy performance implications of that. We're hoping to do that for the next version of the codes and standards enhancement cycle. But I think John presented some data relative to multifamily, and obviously it's highly climate dependent. In terms of what the implications of that are going to be. But for this study, we didn't have a comprehensive analysis of the energy implications of that overventilation, though it's been done, I think, in many other studies.
Yeah, actually, if you get the look at the sensitivity analysis white paper, ventilation rate is one of the variables in that, and we showed it across climate zones. So in the mild climates like Seattle, it's not a very big impact. You can overventilate if you want because it's not very cold outside and it's not very hot outside. In the more extreme climates, it becomes a pretty big number.
Another one for Jim. Maybe a reason why we should split the questions up after each speaker. I'm Robert Greenwald from Prism Engineering in Vancouver. Jim, I know that your concept of dedicated outside air is sort of recommendation for new building, but I'm focused on existing buildings, commercial buildings. I'd like to hear your recommendations about doing evaluations of existing scenarios. How do we assess the overventilation problem, and then what solutions are you recommending? Because installing dedicated stations in the various damper positions in your building for multiple systems can get quite expensive. So practically, what's the ECM? How do we develop it? And what's your recommendations on that approach?
Sure. No, it's a great question. And just to be clear, I'm not talking about dedicated outside air systems in terms of separate systems, separate shafts. But what I am talking about is when we have air handlers, and really down to even the 10 to 15 ton range, can use a fixed dedicated intake for the minimum ventilation rate that's separate from our economizer, and especially on the larger systems, that's pretty common these days with most of the new package systems. So the ECM is to, first of all, to John's point earlier, let's make sure we get our ventilation calculations correct. That's a good place to start. It's really important, but then let's control that with the right system type. And the way that you do that dynamic control is it depends on your system configuration, but we should be able to integrate that into most air handling, typical air handling systems that we see for mid-size and large office buildings, so in retail and hospitality as well. How you control it is again, that's in the nuances, but you can use direct flow station control, so you can actually put a flow station in the outside airstream and control your mixed air dampers directly from that signal, depending on your system configuration. But the important part is that you have some mechanism to do that control directly to change that introduction of air. And then make sure it's part of the sequence. Make sure that it's, that you're not running your outside air system when it's in warm-up mode, or an after-hours cool-down mode. We can control that damper directly and make sure that we're only bringing in outside air and only just enough outside air when we need it. The other thing that gives you, just to add to this demand control ventilation question earlier, is if we have direct flow control, then we can actually change dynamically our flow requirements if we wanted to do it based on occupancy. So it's kind of the next tier. The studies would probably say you would only do this in extreme climates in terms of the cost effectiveness of it. But if you did an occupancy-based control where you change your ASHRAE 62.1 requirement based on the auditorium is now occupied, I need to bring in another 800 CFM, and you could do that directly with a system design that allows you to actually physically measure and control that outside air versus trying to interpolate what that change needs to be at the air handler.
So hi, my name's Joe Pignon with Simpson, Gumpertz, and Hager. And a question for John and Mark. The sensitivity analysis seemed to show, a penalty for too much air leakage or air infiltration, but all your studies in the field seem to show that effect could be really large, up to 7 times. And so I guess I wanted you to speak a little more on what the energy modeling side might be missing as far as what the penalty is for too much ventilation versus what the actual energy audits were showing, like with the corridors. And then as a follow-up to that, any information regarding you had the 1969 building that was using less energy, any thoughts on to what was causing that?
Well, the second question is the central systems were the old building didn't have any. The corridors were unconditioned, so no fans. Plug loads were the same throughout. Water use was the same throughout. Space heating was a little bit higher in the old building, but there was no central ventilation system, so that heat was completely gone. The first question, well, for one thing, it's completely different building types. So the sensitivity analysis was a medium office building, and the data I was showing second, obviously, multifamily buildings. So in the multifamily context for the space heating, ventilation is a huge fraction of that in these buildings because they have a relatively small envelope. Most of these apartments only have one wall with some windows and some wall, and they're surrounded by other apartments. So the envelope portion of the heat loss is relatively small, and the ventilation portion is relatively large. So if you double your ventilation rate, you have a very big impact on the space heating. And in a commercial building, you need more ventilation because there's a higher amount of occupancy. So there's a certain minimum you got to maintain all the time when it's occupied. So it's kind of a different animal, ventilation in an office building compared to a multifamily. I'm not sure I answered your question completely.
I guess I would just add, I think the relationship of ventilation rate and leakage in commercial buildings is sort of the great unknown. There's a lot of studies that have very small data sets that have very wide ranges of conclusions. From, we're underestimating the energy impact of infiltration by, an order of magnitude to it's not that big a deal because we pressurize anyway or whatever. And I think there's a lot more data needed on that relationship for us to really make good decisions. And I think you're going to see more and more testing and attention on air sealing and et cetera to try and get our arms around that. I'm going to take just a moment and ask Davida a question that came up for me. In your sort of final graph, you showed a very high energy use at the swing season, mild temperatures, right? I mean, that was where it was the worst. Did I interpret that correctly?
Yes, what it is a ratio. It's between the consumption and demand. So that shows that when the temperatures are milder, users may use more energy than predicted. Yeah, exactly, and much more than predicted.
Because they're leaving their windows open?
Yeah, too, but also because they are overheating the building very much. And while there is also to say that because it's a ratio, the second value, so the demand value, it's already smaller. It's very small for heating, for example, in October. And if the user then overheat the building 2 or 3 times, or then it is already a bigger ratio. That's also one reason for that.
Another quick question for you. Did you consider not giving the occupants as much control as it sounds like you did?
Well, this is what we want to see. That's why we have the several refurbishment strategies. And we didn't give any feedback yet to the occupants. We will also give them feedbacks, but we're going to show that.
Should be interesting to see how it changes once they hear about that.
Yeah.
Jim, quick one. We were talking about different dynamic strategies, and, to me it seems like you need some sort of zone feedback. I was going to ask you about occupancy sensors, which you just kind of talked to, but other than CO2 and occupancy, is there really anything else we have right now, according to code, to be able to meet code that you can use to change your outdoor minimum rates?
There's really not. The ASHRAE 62.1 technical committee just released a memo. I don't know how wide the circulation is yet, that talks just about using occupancy sensors for the first time to adjust minimum ventilation rates. So that's the first official publication that I've seen, I think, on that.
Can you go to zero?
It cannot go to zero. It can only go to the space-based minimum component. So during expected normal periods of occupancy, you can never go below just the space-based, non-occupant-based component. So I think that we have, according to the codes anyway, the tools that we need to be able to make those decisions between the CO2 sensors and the occupancy sensors. But we're still never, during occupied times, going to be able to go down at the zone level below the minimum ventilation that's needed, even at that zone level. Okay. And that impacts all the way back up to the system level, obviously.
Okay. One more. Sorry, I forgot to introduce myself. I'm Brandon James with the University of Minnesota. But the other thing I found really interesting about your guys' study is, I'd say our biggest user of energy is the occupants themselves and training them. And I see all your thermostat issues. And I have to ask if you ever see, and of course we're Americans and we live free or die, but do you ever see if anybody would ever start to regulate temperature control, with smart thermostats and stuff in residential housing, where we start, and I've always said to my boss, if we can just tell people that, hey, if you're 68, you're fine in the winter, and we just can't ever seem to get anybody at the top to buy into that, and just tell people, don't give them as much control.
I'm more likely to take bold positions like that, like my strategy for conservation of rolling brownouts. But I would say there's a lot of evidence that actually just giving feedback can have substantial impacts on energy use for occupants in residential and commercial space. Just simple feedback, really simple stuff. Dashboards, and the savings are astounding. The studies range from 5 to 30% for just feedback. You don't buy anything except a system for feedback. And I'm not talking about, end use metering of every single thing, just, overall energy use. You're using more than yesterday. How come? Oh, gee, I should do something. It's really astounding. So much as I'm a regulator kind of guy, I think the soft approach of education and data is probably the right approach for occupants.
Hi, David Langford, State Department, and a couple of questions. One, in the high-rise apartment buildings, were the halls, the corridors pressure controlled at all, or was it just turn the fan on, turn the exhaust fan on, you got what you got?
Fans on all the time. You get what you get based on the designer and the installer.
Is there
nobody ever went back to look at it and just?
Yeah, because we're getting ready to start doing some residences, and we're trying to come up with an effective way to do it. Is there a paper that I can get to that you kind of
This,
I can point
yeah,
out saying
well,
somebody's done a study?
this study is, you can see that paper, but there was no agreement on how to size those systems in the engineers that I talked to. Some of them, the one that was using the most energy in the corridor, the engineer said, well, I sized the airflow rate so that it would take care of the lighting load in the summertime so that the corridors wouldn't overheat in the summer. And that flow rate then determined the flow rate for the rest of the year. The common way that those were designed in years past was that the central corridor system was intended to ventilate the units. So the doors were undercut to the corridor, and the corridors were pressurized, and that air was intended to go out through and ventilate the units. Well, fire codes and building codes have eliminated that possibility quite a long time ago. They said, no, you cannot supply air through the corridor for apartments, but it's still commonly being done. So there needs to be we need to get that figured out.
Yeah. Do any of the apartments that you've studied use like the new, new here at any rate, variable refrigerant flow systems? Like for a floor, you could do 6 apartments on one unit, and then that way you'd have the opportunity to move the heating and cooling back and forth between the apartments?
Yeah, not in the type of building that I was looking at in this study in our part of the world. All of those buildings were heating only. There's no air conditioning provided, and most of them are just electric resistance heat. Now, these are all mid-rise buildings, and I just designed a high-rise in Seattle where we did that very thing, used variable refrigerant volume for it. But it's a higher rent, so you can pay for a more expensive system and a lot more glazing. It's big cooling loads. What's that? Oh, in the corridors also the variable refrigerant volume system. We just supplied the ventilation rate, the code ventilation rate, direct outside air, and then treated it at each level.
And then one real quick question for you. You had said for Mark, you'd said something about you were considering doing some code where we were talking about controlling the occupant. Isn't that kind of a gutsy thing that you could say? I mean, how can you create a code before that'll be part of the building construction requirement that's going to tell the builder to control his occupant who he doesn't even know who it might be?
Actually,
seems challenging to me.
What I was talking about is what we call outcome-based codes, and you're given an EUI allowance, and that's what you have to meet. And the enforcement mechanisms obviously have to extend beyond C of O. So you can do it with a bond, you can do it with a tax structure, you can do it with annual inspection, whatever. But there's a bunch of jurisdictions actually adopting it and moving towards it, and I think that's the future, because if we want to get to net zero, we can't just talk about physical aspects of the building. But that means there have to be incentives in place that address occupant behavior, of course, and that is a big challenge. But it is where we got to go if we want to get to net zero. So you'll see more. And actually, I should say, the City of Seattle has adopted a pilot outcome-based code. They're trying to move in that direction. The City of Vancouver, BC has adopted it as code, I think, this month or next month or in a few months. They're going to have an outcome-based code. And part of that means we have to have good targets. So the way we think about it at NBI is that you start with an ankle breaker. That is, there's no penalty except for the very worst performers. And you start moving up so that as we zero in. Right now, we're not in a position to really design because we don't have a very good way to predict actual outcome yet. So we need more and better data.